All right, ladies and gentlemen, good morning and welcome to this panel discussion titled Hot H2O, Global Ocean Warming and Its Implications. We're very happy to see you here. We know that there's a lot of interesting programming going on this morning, and we're grateful that you decided to join us here at the Ocean Pavilion. The Ocean Pavilion is a really wonderful and unique space at COP29. It's where stakeholders, experts, and representatives from industry, policy, NGOs, and academia get together and unite around this common theme of our oceans. And I suppose that we are representatives of the latter of those. We are all graduate students at Scripps Institution of Oceanography that, together with Woods Hole Oceanographic Institution, are lead organizers of this Ocean Pavilion. And we are all going to talk about different aspects of rising sea temperatures for a little bit, and then we are super happy to take questions from the audience, anything related to the oceans that you've ever wanted to ask. Our goal for this is to be interesting, that you'll take away something that you didn't know before, maybe make a connection that wasn't there before. Before we get started, I'm going to let the panel introduce themselves. So, Ella, do you want to start? Tell us your name and what you research.
Hello, everybody. My name's Ella Kim, and I'm a PhD candidate in biological oceanography. And I study fish chorusing, so when many fish sing in California national marine sanctuaries, to better understand which, where, and when fish are reproducing to better protect them. And today I'll be speaking more generally on impacts of ocean heat on marine life.
Awesome. Thanks, Ella. I'm Ben Taylor, also a PhD candidate at Scripps. I study ocean change on large scale, specifically in the Southern Ocean, so mostly looking at the ocean uptake of heat and carbon and the patterns of storage in the open ocean.
Hi everyone, my name's Mitchell Chandler. Like everyone else here, I'm also a PhD candidate at Scripps Institution of Oceanography. My research involves using predominantly ocean observations to examine large-scale ocean currents throughout the water column, so all the way from the surface down to 6,000 meters deep. And today I'm going to be talking about how ocean warming impacts sea level rise.
And my name is Kerstin Bergens, and I'm also a PhD candidate, and I research air-sea interactions and upper ocean dynamics, so the small-scale physical processes that govern how our oceans work, basically, that we actually know surprisingly little about. All right, let's do this. Our oceans cover 71% of our planet, which means that we technically live on planet Ocean rather than planet Earth, right? And this picture here, this map here on the right, is one of my favorite visualizations of this. It's a map where instead of cutting up the ocean, we've cut up the land. And I think it's a powerful visual reminder of the fact that we truly are all connected to the ocean and that the ocean connects us, right? We do this thing where we divide it into the Pacific and the Atlantic and the Indian Ocean, but it really is just one big, the ocean, singular, right? And all of these parts of the ocean connect through various ocean currents, and they talk to each other, all these parts. Now, the climate of our planet is governed by two vast reservoirs of fluid. It's the atmosphere and the ocean, and the way they interact with each other. And we humans, we often move through the atmosphere, right? That's where we drop our emissions and pollution and all of those things. But the atmosphere and the ocean, they talk to each other, and then they exchange things. They meet at this interface, the boundary that we call the sea surface. And it is through this boundary that the ocean has absorbed 25% of anthropogenic CO2 emissions and 90% of the excess heat that is associated with these emissions. And that is what we're going to talk about here today. Now, I said heat. Heat is a form of energy, and one of the fundamental principles, physical principles that govern our world is that heat cannot be created nor destroyed, only transformed. And that means that all the heat that we have put into the ocean, it is not going anywhere. It's going to stay there. Now you may ask, heat. How much heat are we talking about here? And I'm glad you asked, because I have a figure for that. So this figure shows you ocean heat content, a measure of how much extra heat is in the ocean. On the y-axis here, the unit is zettajoules, ZJ. Zeta is a unit that is a 1 followed by 21 zeros. It's a very big number. And joules is a unit of energy, like calories. Similar, if you read on the back of a food label, you might see joules or calories. And what this figure is showing us is that since the baseline of around 1960, the ocean has taken up almost an additional 500 zettajoules of energy. And just for reference, the total global energy consumption per year is about 0.6 zettajoules, which is kind of mind-blowing. Now, what this figure is also showing us is that this heat is not uniformly distributed. So this heat is taken up in different places of the ocean. Before, say, the year 2000, most of this heat was in the upper ocean, so maybe 0 to 700 meters, 0 to 2,000 meters, sort of. But in the last 2 decades or so, we're starting to see a lot of this heat actually being taken up in the deep ocean, below 2,000 meters. And Mitchell will talk more about this in a little bit. Furthermore, if you look all the way to the right, you see that this heat is not taken up uniformly across the globe. So the Atlantic Ocean and the Southern Ocean, which is all the water that connect around Antarctica, they have taken up the most heat. And this has to do with just the way our planet looks. These waters are connected to the poles, the North Pole and the South Pole, and that is where the ocean and the atmosphere exchange the most amount of heat for various reasons. And then heat is then taken up and brought down and distributed at depth. Now, you may ask, how do we figure this out? How do we know that we have this much heat in the ocean? Well, this is actually a very robust finding. We see that this is, maybe it doesn't really work, the laser pointer, but if you look at the left-hand side of the plot, there are a bunch of different lines, and the key point here is to see that they're all roughly aligned with each other. These are all different data sets that were used to compute the same thing, how much heat is in the ocean. Some of them are using in-situ observations, so actual temperature measurements from the ocean, which both Ben and Mitchell will talk more about in a little bit. Others are using satellite data, models, and the point here is that they all agree that this is a robust finding. The ocean is taking up a lot of heat. Now, if we go to the right-hand side of the plot, the shaded area, we can take our estimates of how much heat is in the ocean, and we can run through different projection scenarios or different emission scenarios. And we see that no matter which emission scenario we find ourselves under, the oceans are either going to keep warming or take a long time to cool down. Again, we put this heat in the ocean, and it's not really going anywhere. And this has long-lasting and far-reaching implications for economy, people, various ecosystems that the rest of the panel will now dive into in a little bit more detail.
Perfect. So as we've just heard, the ocean is warming. And one of the implications of this ocean warming is rising sea levels. So using satellite measurements, we've been able to observe that globally, the mean sea level has risen by over 10 centimeters since 1993, with record high sea levels measured this year in 2024. So these rising seas have a number of negative impacts for us and our ecosystems, including but not limited to those on the slide here. So that's increased flooding, loss of ecosystems, freshwater contamination, and coastal erosion. Now these rising seas are driven by two main processes. So the first of these is changes in ocean mass, which is the addition of water from the land into the ocean. And this typically occurs through the melting of ice sheets and glaciers. The second of these processes is steric expansion, which occurs because water expands as it warms. Now, we can use satellites to measure the total sea level, but in order to understand the contributions from each of these terms, so from ocean mass changes and from steric expansion, we need to know what's happening within the ocean, beneath the surface. The main source of present-day measurements of the ocean's subsurface is the Argo program. Now, Argo floats are freely drifting ocean robots that measure temperature, salinity, and pressure as they profile within the ocean. And so a typical Argo profile, which is shown on the slide here, begins with the float at the surface, and it will then descend down to its parking depth, which is typically about 1,000 meters deep. Will then drift with the ocean currents at this parking depth for roughly 9 to 10 days, before then descending down to a set depth and then ascending to the surface. And during this ascent is where it measures these ocean variables such as temperature and salinity, and Ben will also mention some of the other variables that these Argo floats can measure. And so most of the Argo floats that we have in the global ocean measure down to a maximum depth of 2,000 meters. But more recently, we've developed these deep Argo floats. So that's the orange spherical float on the slide here. And these floats can measure 3 times deeper than standard Argo floats, so down to a maximum depth of 6,000 meters. And this means that these deep Argo floats can measure the entire depth of the ocean almost everywhere, basically everywhere except the deepest ocean trenches. Now, using these Argo floats, we've been able to determine that our ocean warming in the upper 2,000 meters, causing steric expansion, has contributed about 1/3 of the total global sea level rise since 2005. But as we heard, the ocean is also warming below 2,000 meters, and this deep ocean warming also causes steric expansion and therefore also contributes to sea level rise. Our current best estimates of this deep ocean contribution suggest that it contributes about 10% of what the upper ocean contributes. But obviously, if you look at this slide versus this slide, we have far fewer measurements within the deep ocean, so below 2,000 meters. And this means that there is a much larger relative uncertainty in the deep ocean contribution. Unfortunately. But in addition to this, the relative contribution of the deep ocean is expected to increase. So steric expansion in the deep ocean is expected to become more important into the future as deep ocean warming continues to accelerate. So far I've just talked about global mean sea level, but it's important to note that there are regional differences in these rates. So it's not a uniform sea level rise over the ocean. And that's shown in this figure, this map up here, which shows the local sea level trends since 2005 relative to the global mean trend. And so that means that a value of 0 on this map doesn't mean that there's been no sea level change. It means that the ocean here has still risen at approximately 3.8 millimeters per year. And these regional patterns that you can see in the rates of sea level rise are predominantly due to regional patterns of ocean warming, which are largely controlled by the large-scale ocean currents and the prevailing wind patterns. But other processes can be important. In particular, uplift or subsidence of land can be really important along some coastal regions. Unfortunately, ocean warming and sea level rise are certain to continue into the near future due to their slow response to greenhouse gas emissions. Our best projections currently suggest that global's mean sea level is likely to increase by between 30 to 100 centimeters by the end of the century. But there are still uncertainties in this projection, in particular in the contribution from the deep ocean and in some of these regional trends. So a global and full-depth Argo array will therefore help to improve these projections of future global and regional sea level rise. But such an array is only possible with sustained international support and funding. And so now I'm going to pass it on to Ben, who will talk about some of the implications at the ESC interface of this ocean warming, and we'll also talk about some of the additional measurements that these Argo floats make.
Awesome. Thank you, Mitchell. Right, so I'm going to speak a little bit about how the ocean being warmer impacts not just the sea level, but also the climate system as a whole, because the ocean is this critical part of the climate system. And in particular, the ocean is the storehouse of energy in the Earth's system. And so you might remember that the ocean takes up about 90% of the heat imbalance caused by anthropogenic CO2 emissions. And that's not because the ocean is warming far, far faster than the atmosphere. It's because the ocean's heat capacity is much, much larger. And so 1 degree of warming, or a temperature change of 1 degree in the whole atmosphere column, 20 or even 50 kilometers high, has the same amount of heat gain as 1 degree of warming in just the top 3 meters of the ocean. But as we heard, the ocean's warming everywhere to at least 100 or 200 meters deep, and in many places to thousands and thousands of meters deep. So this huge heat capacity of the ocean means that the ocean is storing tons of heat, and that gives a lot of momentum to the warming of the climate system. So one example of this is this very important phenomenon that happened in the past 2 years. If you're paying attention to the global mean surface temperature, you probably remember that 2023 and 2024 have been the warmest years on record. But for the few years before that, the Earth's atmosphere did not appear to be warming very quickly, or even might have been slightly cooler than 2020. So why is this? This is very confusing if we think about all of the heat being stored in the atmosphere. But what's happening here is that there's a change in the movement of heat from the ocean to the atmosphere. And this is a climate phenomenon that is known as the El Niño-La Niña oscillation. So if you're from the Pacific region, you may have heard of this because this pattern of climate variability affects the weather across the Pacific Basin and even far away in North America and Antarctica. But what's happening here that matters for the whole globe is that heat is moving very strongly between the atmosphere and the tropical Pacific Ocean. So in the La Niña phase on the left, and even in a normal year, the tropical Pacific in the east is very cool relative to the atmosphere. So it acts as essentially an air conditioning, taking heat out of the atmosphere and storing it into the ocean, allowing temperatures to rise very slowly, even though there's continued net radiation from anthropogenic greenhouse gas emissions. On the other hand, in an El Niño year, like we experienced in sort of winter of 2023 and early 2024, that heat that's been stored in the previous La Niña years in the ocean then comes to the surface. There is a very warm sea surface temperature in the eastern Pacific Ocean, and that allows ocean heat to escape into the atmosphere and lead to dramatic warming throughout the globe. And so this El Niño-La Niña oscillation can explain at least some of this large spike in warming that we saw over the last 18 months or so, alongside a continued warming trend due to anthropogenic greenhouse gas emissions. Another important and critical role that the ocean has to play in the climate system is through when that heat is released, it can empower large storms. And in particular, when the ocean is hotter than usual, it can empower tropical cyclones that can grow more quickly than usual. That ocean heat energy is then converted into powerful winds and strong precipitation events, especially in the tropical regions. So one example in subtropical areas. So an example that's close to home for us as Americans is this surface temperature along, this event that happened, the Hurricane Helene, this September. There was a marine heat wave, which means that the sea surface temperature is much warmer than usual occurring in the Gulf of Mexico, which you see in this left panel. And this allowed this hurricane, Helene, to grow very rapidly because that extra heat in the ocean spurred strong growth of the storm. So that when it hit land in the southeastern United States, it was very destructive. Hurricane Helene killed over 230 people. It cost about $50 billion in damage. And right after another hurricane hit. And so it's this pattern of warming seas driving larger storms, which are more destructive for people and ecosystems there. And I want to emphasize that this is not an isolated event. This is not just a phenomenon in one region, but wherever there is warm ocean, this generates large tropical cyclones. And so you can see in this map here, there are a bunch of lines, and what those are all the paths of tropical cyclones in the historical record over the past century. And the color indicates how strong those cyclones are. So you can see that in the regions of warm ocean off the equator, there tend to be stronger and stronger cyclones as they grow, as they travel westward. And that's because the ocean or the storms are picking up energy from that warm ocean. But then you'll notice that as soon as they hit land, the energy source from that warm ocean is no longer present and the storms quickly drop off. And this is because ultimately these huge storms that have humongous societal and economic impacts on nations are coming not from that nation itself, but from the ocean near it. And so as the ocean continues to warm under climate change, we will still see typhoons and hurricanes, but those typhoons and hurricanes will be even stronger than before because they are able to get more energy from a warmer ocean. Right, so 2023 was a very an important year for the global climate, but I wanted to share some news that you may not have heard from where I study, which is the Southern Ocean. So 2023 to 2024 was also a very scary year for Southern Ocean scientists because we saw the impacts of marine heat on the sea ice system. So the Southern Ocean, as Justin mentioned earlier, takes up a large amount or a disproportionate even amount of heat from the atmosphere because it's a place where surface waters can enter the deep ocean and bring that atmospheric heat into the ocean. And this has a good effect in a way for the atmosphere in the southern hemisphere because it's been warming more slowly than most regions in the globe because of that cooling that comes from ocean subducting heat or bringing it into the deep ocean away from the atmosphere. And so for a long time, there was a pretty mild and even increasing trend in the upper right of the Antarctic sea ice extent. So whereas the Arctic sea ice has been declining rapidly over the past 40 years, the Antarctic did not have much change until 2015 because of the slower surface warming. But this has begun to change. That heat that was not at the surface because it was taken into the deep is accumulating in the Southern Ocean. And as you can see, over the past 15 years, there's been a marked increase in ocean temperature in the Southern Ocean, and also a marked decrease in the amount of sea ice. So what's happening here is that ocean heat is coming up to the surface and melting the Antarctic sea ice. And as the sea ice begins to melt, it sets off a range of feedbacks. There's less sea ice, then maybe the ocean has less of a reflective covering and takes up even more heat. There's warming, and we may enter a new low sea ice state in Antarctica with a lot of impacts for the ecosystems. One other piece that I wanted to share, that the Southern Ocean is how the Southern Ocean is affecting the global climate, is through taking up not only heat, but also anthropogenic carbon emissions. And so those same processes that are taking water from the surface into the deep ocean will also subduct carbon emissions into the deep ocean. And this means that the ocean is then moderating the climate change that the world experiences because we have less carbon in the atmosphere. At the same time, that comes at a cost, right? Because as the ocean takes up carbon, it also decreases in pH. This is a process known as acidification. And we can see over time that in the Southern Ocean, as the waters have taken up more carbon from the atmosphere, the pH has grown lower over time. I also wanted to share a little bit, how do we know this? This is me on the right, and I'm putting in the water what's called a BGC Argo float. BGC, so it's like an Argo float that Mitchell mentioned, but the BGC stands for biogeochemical, which means it's taking biological and chemical parameters in addition to temperature and salinity. In particular, it's measuring pH, oxygen, nitrates, chlorophyll, and particulate matter, all of which taken together can help us constrain how much carbon is being taken up and stored in the ocean instead of the atmosphere, and how is that changing over time as global warming continues. And so you can see the surface ocean has taken up a lot of carbon over the past 30 years, as we've learned from these float measurements. And that is most strong at the surface, but even extends to the deep ocean, with impacts for creatures. And to talk more about that, I'd like to invite Ella up to share.
Okay, so we've heard a bit about how ocean warming is impacting both sea level rise as well as fueling big storms, and then also leading to ocean acidification. And so I'm going to speak a bit more on how all of these factors are then impacting the creatures that live within the ocean. So this is just really the tip of the iceberg, but I'll be touching a bit upon coral reef ecosystems, as well as shifts in species distributions, and then lastly, changes in marine food webs. Okay, so to start out with coral reefs, the first impact when we think about marine heat on coral reefs is bleaching. And when we think about corals themselves, corals are colonial organisms, and each individual is called a polyp. And within that polyp, we have zooxanthellae, which are these tiny algae that photosynthesize for the coral. Just like land plants that photosynthesize, photosynthesis produces sugars, or glucose, and that's food for the corals. Now, during times of intense marine heat, like during marine heat waves, we get bleaching. And this is when the ocean is hot, the zooxanthellae algae that live within the corals will be ejected out of the polyps. And the zooxanthellae are what cause corals to be beautiful and colorful. And so you can see in this picture of corals in National Marine Sanctuary of American Samoa, a healthy reef on the left side, and a bleached reef when the zooxanthellae have been ejected. Now, when these marine heat waves are persistent, when they last for a long period of time, the corals are without their zooxanthellae and without food, which, if is for too long, can be permanently ejected and bleached, at which time we can have algae and crusting algae taking over and killing these corals. Now, the second big whammy on coral reefs is ocean acidification, which Ben spoke about earlier. And with ocean acidification, as the oceans are becoming more acidic, think like vinegar, we have less carbonate available in the ocean. Now, calcium carbonate is really important for a lot of the shelly organisms in the ocean, as well as for corals, because corals build their skeletons out of calcium carbonate. Now, when the ocean is acidic and there's less calcium carbonate available, corals lose the ability to grow and build their skeletons. This is so catastrophic because coral reefs provide incredible amount of structure for lots of different types of organisms, from fish to invertebrates. And then the last factor here that I'm going to touch on for coral reefs is hypoxia, or deoxygenation, low amounts of oxygen. So a recent study from Scripps Oceanography looked at around 30 reefs globally and found that 84% of reefs are already experiencing hypoxia, or these low oxygen conditions, which is really detrimental to their health. And over the next century, under the worst warming scenarios, we find that this most severe hypoxic threshold will be reached 3 times more frequently across these reefs globally. Now, this triple whammy of both bleaching, acidification, and hypoxia is really impactful because coral reefs support such incredible biodiversity and also protect ocean coastlines. So to speak a bit more about biodiversity, although coral reefs don't take up that much real estate, only covering 1% of the ocean floor, they host or provide essential habitat to 25% of marine species, which is really striking. And then beyond that, and which you can see in this beautiful picture, and then also beyond that, coral reefs also buffer wave energy. So when we think about these ocean heat fueling big storms that Ben spoke about, our coral reefs help to buffer that wave energy. So when we have these big waves coming in through tropical storms, coral reefs act as these guardrails to help buffer out that wave energy to protect coastal communities and small island communities from both flooding and coastal erosion. So our coral reefs are important amongst the many other important marine ecosystems. And then beyond coral reefs, we also have impacts of ocean heat on changes in species distributions. And I'll speak to one example of that coming from a recent study from Scripps Oceanography, still in prep, from the Scripps Whale Acoustics Lab, where they gathered decades of underwater sound data from across Southern California in order to study whales. Collecting sound data is a great way to study whales because much of the ocean is dark, and so whales use sound to communicate with each other. So they collected decades of ocean sound data from across Southern California, and what they found was that during these intense periods of heat, namely from 2014 to 2016, there was this intense marine heat wave, which we call the blob. And during this time, fin whales and blue whales were found to be vocalizing much more in our further north sites in cooler waters. So we found that their presence of fin whales and blue whales were shifting further north during these times of intense marine heat. And while this is one example of blue whales, fin whales shifting their distributions with warming waters, this isn't limited to just whales. We see these changes in species distributions from ocean warming across the food web, from the tiniest of plankton to the biggest whales and sharks and fishes. And then more on the marine food web here. So with ocean warming, we also see huge changes in marine food webs. This is a really simplified marine food web here on the left-hand side. On the bottom, we have our phytoplankton, which are our plant-like photosynthesizing plankton. Plankton are, for the most part, tiny organisms that can't swim against a current. And then on top of that, we have our zooplankton, or our animal-like plankton. And then we have our small fishes and squid, and then at the top, our large apex predators like tunas and sharks. And here I'm going to highlight our zooplankton at that second level, which are really important connectors of energy from phytoplankton up to our big fish. And what we're finding with ocean warming is that our zooplankton communities are shifting from being filled with things like copepods and krill, which are very crunchy, munchy, lots of calories and protein for fish, to more jelly-like. Think jellies, siphonophores, salps, and whatnot. And with that, this of course really impacts fish because we have decline in food quality. I think it takes much more jellies to fill up than when you're eating more shrimpy type things. And this recent study from Hennigan et al. Found that, so if we see the plot on the right-hand side, for the different emission scenarios in different colors, we see, and over time on the x-axis, the greatest shift change in biomass of zooplankton communities over the next century under the worst emission scenarios. So look at that pink line, we see the most drastic change in zooplankton biomass, shifting from our more nutritious copepods and krills to more presence of our jelly-like organisms. And this, of course, leads to declines in food quality of fish, which then impacts lots of people in our fisheries, of which 3 billion people worldwide are dependent on fish for their primary protein source. So I hope this kind of gave a highlight as to how the physical oceanography that we spoke about in regards to ocean warming then impacts the creatures that live within the ocean, and then impacts all of us. And then Shashtan's going to wrap us up.
Thank you. Yeah, and to close this out, we'd just like to reiterate again that our oceans are warming due to anthropogenically driven global warming. And that all the heat that we've put into the atmosphere is eventually going to trickle down to the oceans with far-ranging and long-lasting implications for ecosystems, for humans, for coastal communities, for global communities, not just those people living near the ocean. And in order to fully understand, to be able to better project, mitigate, and adapt to these changes, we really do need scientists and policymakers come together and ensure that a lot of these observational programs, a lot of these data collection programs and research programs that are essential for understanding the science behind this continue to be supported and funded and internationally collaborate around. Because again, the ocean is all around us and we are connected through the ocean. And with that, we say thank you for paying attention, and we're happy to take any questions that you might have.
Kind of. Oh, there we go. Hi, great talk, by the way. I am very curious as to why there is a shift to these more gelatinous type of organisms over the more like nutritious protein-filled like shrimp and krill, and how the ocean warming is actually driving that.
Yeah, thanks for that one. You can all hear me. Okay, so there's a couple different hypotheses as to why this might be happening. Namely, so when we have the warming of the ocean, what we have is the ocean becomes quite stratified. What that means is if you think of like a layered cake with distinct layers where we have less mixing. And when we have that, we have a number of different things happening. So ocean is warmer. Also, we have more layers of expanding layers of low oxygen or oxygen minimum zones and whatnot. And essentially a number of things, but jellies do really well, or a lot of gelatinous organisms, jellies and salps do really well in warm water. They also do really well in low oxygen conditions. And essentially they have this kind of like boom or bust reproduction where they're able to reproduce really quickly and kind of outcompete the other zooplankton. They can reproduce much more quickly. They're also not very picky about what they're eating as long as they can fit it within their orifice. And so they're able to kind of beat out the other plankton under these conditions. Essentially, they're not that picky. They can do really well in like really hot and cold and really acidic and changing low oxygen conditions.
The Atlantic meridional overturning circulation has been in the news a lot lately, and I'm curious what your research has to say about that, or if that's a direct thing that you're looking at. I'm just curious.
I think we might all be able to comment on that a little bit. So yeah, the meridional overturning circulation, or sometimes also referred to the global ocean circulation or the global conveyor belt. It is this this way of describing the ocean as a transporter of heat. Mitchell is finding a photo. The way the ocean takes in all the heat that gets put into it from the sun and redistributes it across the ocean. And in essence, warm water is flowing from the equator where it gets hot, and it flows towards the poles where it's cold, and the ocean gives off heat to the atmosphere, which is why we can live at high latitudes, because the ocean is giving us a little bit of heat from the equator. And then the water at the poles gets cold. It sinks because it gets heavy when it's cold. It sinks down, and then it flows back towards the equator along the seafloor and comes back up again. And one of the most the biggest branches or the biggest parts of this circulation is the circulation in the Atlantic Ocean that brings heat from, again, the tropics or the equator north to the Arctic. You have probably heard of the Gulf Stream, which is the part in the Atlantic. The Kuroshio is the current, primarily in the Pacific, the equivalent. And yes, so AMOC, the Atlantic Meridional Overturning Circulation, is something that we've been researching for a long time, the scientific community. For those of you who have seen the movie The Day After Tomorrow, that is what's happening in that movie, that current stops and everything gets very cold. And yeah, although there has been some debate over the back and forth over the past decade, because scientists like to debate and disprove each other, there is at this point pretty solid evidence for the fact that this part of the global circulation is changing. There is some between years variability, but overall it is changing and slowing down, and that will have implications for climate in the Northern Hemisphere, particularly Europe and North America. And it's still we have a set of moorings, for example, in the Atlantic Ocean, a bunch of different research programs that have been on the scene for about 10, 20 years, kind of. So it's still, we know some things, but we also don't know, we know about variability on that scale, but it's hard for us to predict exactly what's going to happen, future, really long term. But yeah, it is changing, and there will be consequences.
And the reason I pulled this slide back up is, as I said, the regional variability that we see in these rates of sea level rise is predominantly related to changes in ocean warming. And so you can see evidence for the slowdown of the AMOC really clearly if you look in the North Atlantic there. So you see this sort of dark blue blob, which means that sea level is rising slower there, or possibly not at all. And this is basically related to this region warming less fast or even cooling. And this is because of this slowdown in the AMOC. So less heat is being transported as far north, which is then related to why we see such drastic warming and sea level rise slightly south of this blue blob. So this heat that used to be transported further north and then descends in this AMOC branch is now staying within the subtropical gyre and recirculating around there. So this is one of the additional sources of evidence that we have for the slowdown of the AMOC.
Yeah, and I'll just quickly add, I did some work looking at future projections, and we were trying to understand why in the future we see a band of warming even in the southern Indian Ocean, so almost kind of between South Africa and Australia. And what we found out about that, we were testing all different kinds of things that might be affecting the Southern Ocean. It turns out in the future climate scenarios, the changes that we're seeing in the North Atlantic actually propagate across the Atlantic Ocean almost to the opposite side of the world and are a main driver of this strong warming in the Southern Indian Ocean. So it just really highlights what looks like a regional or small change that might just hit Europe ends up affecting the whole global climate in ways that are very surprising even to scientists now, and just highlights the interconnected nature of the climate system. Thanks.
Thank you. Yeah, thank you so much for this talk. It's great to hear some of the science behind our warming oceans and the implications of that. I was wondering if you could talk a little bit about different ways, research, technology, policy, things that could help us lower the rate of warming in our oceans.
Turn off the faucet. Stop heating the atmosphere, and that's how you're gonna cool down the ocean. Right, the oceans, like Ben talked about, have a different heat capacity. It's both the atmosphere and the ocean are fluids, but they have very different properties. So it takes a lot. It's a lot easier to heat and cool the atmosphere than it is to heat and cool the ocean. And for a while, the fact that it takes more to heat the oceans has been a bit of a buffer in our climate system. It's helped us mitigate some of that heat that we put into the atmosphere. But yeah, it's also harder to take heat out of the oceans. Yeah, turn off the faucet. And yeah, I don't know if you guys have anything else to add to that.
Reduce emissions, greenhouse gas emissions too.
Yeah, but it's a good question. Solution oriented, I like it.
Yeah, and then we'll do Tom.
Yeah.
Great presentation from all of you, those that I have heard, but very good to understand the details of it. But in the day after tomorrow, the movie, it's triggered by a sudden temperature drop that they notice in data coming in. So my question from a climate perspective, what you see holistically, where are we lacking most data from the ocean? So if you had 100 million, whatever, where would you invest it to get a better understanding of the state of the ocean from a climate perspective? So that's question number one. And question number two, for your specific own research and work, what data are you missing? Where would you put the money?
That is a great question. Mitchell, do you want to start?
Yeah, I absolutely have thoughts about that. So I talked a lot about the Argo program, and Ben also mentioned that as well. And that is our main source of subsurface measurements within the ocean. The upper 2,000 meters is pretty well sampled. Obviously, that needs to continue, but then BGC, which Ben talked about, and I'll let him talk about more after this as well, that isn't global. Well, it isn't global at the coverage that we would like. So we would want to obviously increase the density of these BGC floats in order to understand carbon uptake around the globe. And likewise, also the deep Argo floats that I mentioned as well. They're currently basically in a pilot phase still, deployed in some of the basins where we see the most substantial deep ocean warming, but the deep ocean is hugely undersampled. So again, if we could sort of expand that array with global coverage from essentially the sea surface to the sea floor, would help immensely in our understanding, and in particular in understanding some of this regional variability that we see, say in sea level rise. Regionally, the deep ocean can be really important in steric expansion, ocean warming, even though globally it only contributes about 10% of current sea level rise. Did you want to add anything about BGC?
Yeah, I would agree with that. I think every scientist probably has their answer of what they think the most, important is. But yeah, certainly for my research, and I think also for society in general, really being able to accurately know how much carbon is in the ocean versus in the atmosphere? Because the ocean has sources and sinks emissions just like every country, right? And those are not well constrained and measured at the moment. We have a system that's growing, that's getting there, but we need more data. Much of the open ocean is not well sampled, especially for carbon chemistry. And so I would emphasize that somewhat selfishly, but also because I think it matters to a global government.
And how many Argos is it currently in the Southern Ocean, the area you're focusing on?
The data I was showing in the Southern Ocean is a product of about 200 floats, at different times over the past years. Maybe a little more than that, maybe 250. There's a goal to have a global array of floats. That's about 1,000 that are at depth, and then there are also drifters at the surface, which I couldn't give you a number on. Yeah.
And I did want to add something else to that about the Argo program. I'll pass to you after, Ella. So we've talked a lot about the science that it basically enables, but a part that I didn't mention is it's one of the main source of data into like weather forecasting on like day-to-day, weekly basis. Like if you look at this map, right, and as Shushton mentioned, the ocean covers most of the globe. And we have much fewer measurements of the ocean than on land, but it controls weather a lot. And so in order to initialize these weather forecast models, we pull data from the Argo program quite heavily to provide the initial state when we run these models. So it's not just science that it's important for. Like if you've ever looked at a weather forecast, you've indirectly used this Argo data.
Oh, I guess I'll just add that while the Argo program has really great geographic coverage, like as a whole, as a scientific community, the global south lacks observation, and so resources really need to be input into oceanographic measurements and putting resources into oceanographers who are doing measurements in the global south. So that's one thing. And then I'd say in terms of biology, at least with acoustics, acoustics is awesome because, you know, we dump a recorder or hydrophone, which is like a microphone listening at the bottom of the seafloor, and it can sit there for six months at a time, which is a long period of time. But we need to continue to build these time series because when you're looking at things like impacts of climate change, we need super, super long, many decades of data in order to get any type of signal on when whales are singing less or when fish are impacted by marine heat waves. Having long time series is so, so valuable.
Yeah, I would sum that up and say that, yeah, we need support. If I had $100 million or however lots of money for ocean research, I would put it into continuing a lot of these international collaborations around global ocean measurements like Argo, like surface drifters, and then also put it towards making sure that this data is useful and accessible to everyone, and that the knowledge is spread and also, you know, given to the communities that need it the most. Yeah. And you had another question at the beginning. You had two questions. That was your second question. What was your first question again?
That would be about day after tomorrow, but
the day after tomorrow.
No.
We'll talk more about that. Yeah.
Another gap was on science and policy you mentioned in your closing, and what is really the way to connect these two, because that's extremely important to bring the knowledge this community has to everyday politicians that sits on the on the steering wheel often.
Yeah, and to make sure that the knowledge goes both ways, right? Because we are scientists and we're good at collecting data and writing papers, and then you have policymakers who are good at international negotiations and writing steering documents, et cetera, and we need to be able to communicate what we learn about the ocean, but we also need to listen to what people need to know about the ocean in order to be able to make those kind of policy decisions. So there needs to be a better flow of information both ways, and being here at COP is hopefully one of the ways that we can start that channel of communication. Yeah. There was a question from Tom.
Hi, Tom Corringham, also at UC San Diego. Thank you for the presentation. What kind of terrifies me are the feedback loops and the potentially irreversible impacts. And I know, Sharston and Mitchell, you mentioned AMOC, which would be irreversible, at least in our lifetimes or on a century or millennial scale. Ben, you mentioned the feedback with ice sheets and potential albedo impacts there. And Ella, you mentioned coral bleaching. I'm wondering if if you could speak to these feedbacks and irreversibilities, or if there are other examples that keep you up at night.
Do you want to tell us about your nightmares, Mitchell?
I don't remember my nightmares. I try to forget them. I don't know. I don't really have anything else to add to that. I'm going to think on it more, but if anyone else wants to...
I can shoot. Totally. So, with climate feedbacks, there is a change that builds on another change, say reduced sea ice cover allows more heat into the ocean. The ocean gets warmer and it holds that heat over time. And then sea ice grows slower in the next winter. That is ice albedo feedback that we've heard about, and is seen in the Arctic, how it's been really causing a lot of persistence. I'd say like some things like deep ocean warming are, I think, truly or like for millennia scale irreversible, because once something is deep in the ocean, it is going to stay there for a long time, and there's no contact with the atmosphere. And so things like AMOC, where or these deep ocean currents, there's a really strong sense of we can't do much about it. I would emphasize, though, that even like models often show an AMOC recovery on the order of 20 to 30 years if there's a change in the surface forcing, because the atmosphere can change quickly, and the ocean has memory of many years, but at the surface there is a good deal of possibility of change on sort of decadal timescales. And so I think I would emphasize that if the atmosphere cools, surface processes can recover. Another example that just came to mind is like ecosystem changes can be very destructive, but a nice thing is that like the ocean phytoplankton will bloom anew each spring, and things like this. Like there is a lot of possibility if the surface conditions are restored to something that's more normal, that at least the surface ocean can recover relatively quickly. Deep ocean warming will continue, and heat that's down there is not coming back up for a long time. But I think the ocean, the climate system can recover in a lot of ways if we give it an opportunity to recover, and so I would emphasize that.
Yeah, and I was gonna draw a parallel to ecology, where we often talk about ecosystems and different stable states. Like an ecosystem can go through a change if a predator disappears or something shifts in the favorable conditions for different species, and we enter a new stable state with that looks different from the previous states. We often probably heard the concept of a tipping point, right, that we're approaching, and it's often pictured that's this little hilly situation with a ball that gets pushed up a hill and then it rolls down a hill and it ends up in a new place, right? And we can't push it back up the hill because it's irreversible, but we find ourselves in a new state, a new stable state. And with some of these changes that we're going through or that we are causing in our climate system, it is likely that we find ourselves in a new stable state, a new normal, and what exactly that is going to look like is we don't know yet because we don't have the data. But again, another argument for making sure that we keep collecting the data, that we keep doing the science, and that we keep researching our planet, and we keep talking about it. And with that, we are actually at time. So I just want to say thank you again for coming and for sitting in and listening. If you have any more questions, feel free to come and talk to us, and enjoy the rest of your day at COP. Thank you.